At 08:43 on a humid morning in 1943, that illusion vanished. Somewhere above the endless blue waters near New Guinea, a lone American fighter pilot glanced through his canopy and saw a shape every Allied aviator recognized immediately. Thin wings, rounded tips, lightweight frame, fast in a climb and deadly in a turn. A Zero. The Japanese fighter rolled hard to the left. The American pilot instinctively tightened his grip on the control yoke. Every briefing he had attended echoed in his mind. Do not turn with a Zero. The warning existed for a reason. Since the opening months of the Pacific War, Japanese fighter pilots had built a reputation that bordered on myth. Their Mitsubishi A6M Zero could carve through the sky with astonishing agility. Allied pilots who tried to match those turns often found themselves staring down gun barrels moments later. American doctrine emphasized something different. Use speed, use altitude, use diving attacks, strike and climb away. Never get dragged into a turning contest. Yet that was exactly what was happening. The Zero banked sharply, attempting to force the fight into a tight circle. The maneuver was familiar. Japanese pilots had used it repeatedly across the Pacific. The goal was simple: make the heavier American fighter bleed energy until it became an easy target. The pilot knew the trap. He had seen it before. He had heard stories from squadron mates who never made it back. For a brief moment, he expected to feel the usual resistance from his aircraft. He expected the controls to fight him. He expected the nose to lag behind the turn. Instead, something felt different. The aircraft responded immediately, not dramatically, not violently, just differently. The movement felt smoother, more predictable, almost lighter. His eyes narrowed. Something was wrong. Or at least, it felt wrong. For a split second, he wondered if combat stress was affecting his judgment. The twin-engine fighter beneath him was a P-38 Lightning, one of the most recognizable aircraft in the American arsenal. Its distinctive twin-boom design, concentrated nose armament and long-range capability had made it a valuable asset across the Pacific theater. But no pilot ever confused a P-38 with a Zero. The two aircraft represented opposite philosophies. The Zero was built around simplicity, lightweight, and maneuverability. The P-38 was larger, heavier, and packed with equipment. Twin Allison engines generated thousands of horsepower. Turbo superchargers allowed high-altitude performance. 4 50-caliber machine guns and a 20-millimeter cannon sat concentrated in the nose. On paper, it looked formidable. In combat, however, pilots often discovered that paper and reality were not the same thing. The Zero continued its turn. The American followed, then followed again and again. Seconds passed. The expected separation never came. The Japanese pilot should have been pulling away. Instead, the distance remained almost unchanged, a few hundred yards. Then less. The American pilot felt a strange mixture of excitement and confusion. This wasn't how the engagement was supposed to unfold. The Zero's pilot appeared to realize it too. The Japanese fighter suddenly reversed direction, attempting another maneuver designed to force an overshoot. Again, the P-38 stayed with him. The response from the controls felt natural, predictable, almost effortless. The pilot wasn't fighting the aircraft anymore. He was simply flying it. That subtle difference changed everything. The engagement tightened. The Pacific sky became a spinning blur of blue water, white clouds, and flashing metal. Both aircraft were now operating near the edge of their performance envelopes. Small mistakes mattered. Tiny advantages mattered even more. The Zero pilot had spent years training for this kind of fight. He trusted the aircraft beneath him. He trusted the doctrine that had worked repeatedly against Allied opponents. But doctrine only works when reality cooperates. On that morning, reality was beginning to shift. The American fighter remained in position. The firing solution improved. The distance closed further. The Zero banked again. The P-38 answered immediately. No hesitation. No delay. The American pilot still couldn't explain why. He only knew that his aircraft felt different from every previous mission. Different enough to notice, different enough to survive. Later, after the mission ended and the adrenaline faded, he would try to describe the sensation to maintenance crews. The controls felt smoother. The aircraft felt more responsive. The handling felt cleaner. It was as if somebody had quietly adjusted the rules of the fight. What he didn't know was that somebody had. Not a famous engineer, not a decorated ace, not a team of designers working inside a stateside factory. A mechanic, an ordinary mechanic working long hours beside a remote Pacific airstrip. A man whose name would never appear in newspaper headlines. A man who had listened carefully when pilots complained. A man who had noticed a problem others ignored. And a man who had installed a simple piece of wire that many people considered ridiculous. At first glance, the modification seemed too small to matter. Certainly too small to influence aerial combat. Yet somewhere above the Pacific, one pilot was unknowingly proving otherwise. The strangest part was that he initially believed something had gone wrong with his aircraft. The truth was exactly the opposite. His airplane wasn't broken. For the first time, it was working closer to the way it always should have, and that raises a question. If a simple piece of wire could change the feel of one of America's most advanced fighters, what problem had been hiding inside the P-38 all along? To answer that, we need to understand the Lightning's biggest weakness. The Lightning had the power. It didn't always have the control. To understand why that seemingly insignificant piece of wire mattered, we need to step back and look at the war that produced the problem in the first place. By 1942, the Pacific had become a battlefield unlike anything military planners had imagined before the war. Distances were measured not in miles but in oceans. Pilots weren't simply crossing front lines. They were crossing entire regions of the world. An American fighter mission might begin before sunrise and continue for 6, 7, even 8 hours. Some flights stretched beyond 1,000 miles. A navigation error of only a few degrees could leave a pilot searching endless water for a tiny island airstrip. A mechanical failure often meant a parachute landing into open ocean. There were no emergency roads below. No friendly villages. No second chances. The Pacific punished mistakes. That reality shaped every aircraft sent into the theater. The United States needed a fighter capable of reaching targets that most contemporary fighters couldn't even approach. It needed range. It needed firepower. It needed altitude performance. And on paper, the Lockheed P-38 Lightning appeared to be the perfect answer. Even parked on a runway, the aircraft looked different from everything around it. Twin booms stretched behind the wings. A central nacelle housed the pilot. 2 Allison V1710 engines produced more than 2,800 horsepower combined depending on configuration. Turbo superchargers allowed the aircraft to maintain performance at altitudes where many rivals struggled. Its concentrated nose armament removed the need for wing-mounted gun convergence. 4 50-caliber machine guns and a 20mm cannon could deliver devastating fire precisely where the pilot aimed. The aircraft could climb rapidly, dive quickly, carry fuel for extraordinary distances. By nearly every measurable statistic, the Lightning looked like the future. Many American pilots loved it. Many Japanese pilots respected it. Yet war has a way of exposing weaknesses hidden beneath impressive specifications. The Pacific was about to reveal one. The problem wasn't speed. The P-38 could exceed 400 miles per hour. The problem wasn't firepower. Very few fighters wanted to remain in front of its guns. The problem wasn't range. In some missions, Lightning pilots traveled farther than entire European fighter operations. The problem was what happened when combat stopped following the plan. Military doctrine is neat, combat is not. American tactical manuals emphasized energy fighting. Pilots were trained to use altitude, speed, and diving attacks to exploit the Lightning's strengths. The theory made perfect sense. Attack from above, strike quickly, use superior speed to disengage. Repeat. Avoid prolonged turning battles. Simple. Except enemy pilots had plans too. Japanese aviators flying the Zero understood exactly what the Lightning wanted. Whenever possible, they tried to drag engagements into slower, tighter maneuvering contests. This is where the contrast between the two aircraft became impossible to ignore. The Zero had been built around maneuverability. Weight reduction influenced almost every design decision. The aircraft could pivot through the sky with remarkable agility. At lower speeds, it felt almost effortless. The Lightning represented a different philosophy. It carried more fuel, more equipment, more firepower, more structure. The result was a fighter that excelled in some areas while demanding more from its pilot in others. When combat devolved into low-speed maneuvering, some pilots reported a recurring frustration. The aircraft wasn't unresponsive, it wasn't dangerous, but it didn't always feel predictable, especially when conditions became chaotic, especially when fatigue entered the equation. And fatigue was everywhere in the Pacific. Imagine sitting inside a cockpit for 6 hours. The tropical sun heats the canopy. Humidity rises. Sweat soaks flight gear. The constant vibration of twin engines becomes background noise. Navigation calculations continue for hundreds of miles. Eyes scan empty horizons searching for enemy aircraft. Then suddenly, without warning, the workload explodes. A few seconds earlier, the pilot was cruising. Now he's fighting for his life. Every control input matters. Every decision matters. Every delay matters. Under those circumstances, even small handling characteristics become significant. Pilots began describing similar experiences after returning from missions. The comments varied, but the pattern remained. Some aircraft felt better than others. Some seemed smoother during specific maneuvers. Some felt slightly more responsive during combat. The differences were subtle, too subtle to immediately trigger alarm, too consistent to completely ignore. The challenge was identifying the source, because maintenance crews faced countless variables every day. Salt air attacked metal components. Coral dust infiltrated mechanical systems. Heat expanded materials. Humidity affected equipment. Aircraft returned from combat with bullet holes, worn, parts, damaged panels, and unexpected maintenance issues. Determining whether a handling complaint represented a serious problem or normal variation wasn't always easy. Many concerns disappeared during inspections, others could never be reproduced, and some remained mysteries. Meanwhile, the Pacific War intensified. New Guinea, the Solomon Islands, the Bismarck Archipelago. Every month seemed to introduce another operation, another island, another stretch of ocean. Pilots kept flying, mechanics kept repairing, commanders kept demanding results. And somewhere in that cycle, a small observation began repeating itself. Not once, not twice, but often enough to attract attention. A pilot would return from a mission and mention a control issue. Another would describe a similar sensation. Then another. The comments rarely sounded dramatic. No one claimed the aircraft was failing. No one demanded an emergency redesign, but experienced mechanics know something important. Machines often whisper before they scream. The most valuable clues are frequently the smallest ones. A vibration, a noise, a hesitation, a pattern. Most people dismiss those details. Good mechanics don't. One particular mechanic working long hours on a remote Pacific airfield started noticing the pattern. At first, it seemed insignificant, just another pilot complaint at the end of a long day. But the more he listened, the more familiar the stories became. Different pilots, different missions, different aircraft, yet somehow the same observation kept resurfacing. The lightning had tremendous power, but under certain conditions, something about its control behavior didn't feel quite right. Most people heard complaints. He heard a problem waiting to be solved, and after enough missions, enough maintenance shifts, and enough conversations beside sun-bleached runways, he became convinced that the answer wasn't sitting in a factory thousands of miles away. It was sitting right in front of him. He just needed to find it. One mechanic kept hearing the same complaint after every mission. He wasn't trying to redesign the aircraft. He was trying to keep it flying. That distinction mattered. Because when people imagine wartime innovation, they often picture engineers gathered around drafting tables in clean offices. They imagine teams of specialists surrounded by blueprints, calculations, and technical reports. The reality of the Pacific was very different. Thousands of miles from American factories, aircraft maintenance often happened on rough coral airstrips carved out of jungle terrain. There were no spotless hangars, no endless supply chains, no comfortable offices with controlled temperatures. There was heat, humidity, dust, mud, and an endless stream of damaged aircraft returning from combat. The mechanic at the center of this story worked in that world. He wasn't famous. He wasn't a test pilot. He wasn't a senior engineer. Most of the time, nobody outside his squadron even knew his name. His days started before sunrise and often ended long after dark. The Pacific climate punished both men and machines. Coral dust drifted into every moving part. Salt air accelerated corrosion. Heavy rain transformed airfields into muddy obstacles. Yet every morning, aircraft still had to be ready. Pilots expected engines to start, controls to move, weapons to fire. The maintenance crews made that possible. Few people appreciated how demanding the job truly was. A pilot might spend 6 hours flying a mission. The maintenance team could spend twice that long preparing the aircraft before it ever left the ground. Every cable, every pulley, every control surface, every hydraulic connection, every fuel line, everything required inspection, and because combat damage was common, no 2 days looked exactly alike. One aircraft might return with bullet holes in the wing. Another might have engine vibration problems. Another might have damaged control surfaces. Each issue demanded attention. Each repair demanded judgment. That constant exposure gave mechanics something valuable. Pattern recognition. Pilots experienced an aircraft for a few hours at a time. Mechanics saw dozens of aircraft every day. They noticed trends others missed. The mechanic began hearing the same comments repeatedly during post-mission inspections. Not dramatic complaints, not emergency reports. Something subtler. Pilots described the aircraft as feeling heavy during certain maneuvers. Others mentioned inconsistent control response. Some couldn't explain the sensation at all. They simply knew that one lightning felt different from another. At first, the mechanic dismissed the reports. Combat pilots often returned exhausted. Fatigue affects perception. A 6-hour mission over open ocean could leave even experienced aviators mentally drained. Small differences might simply be pilot preference. Yet the comments continued. Weeks passed. The pattern grew stronger. The same observations appeared from different pilots who had never discussed the issue with one another. That was what caught his attention. Independent reports often reveal real problems. One complaint can be coincidence. 20 complaints rarely are. The mechanic started paying closer attention. After each mission, he listened carefully during debriefs. He asked questions. When exactly did the aircraft feel different? At what speed? At what altitude? During what maneuver? The answers weren't always precise. Combat memories rarely are. But gradually, a picture began to emerge. Something about the aircraft's control behavior seemed inconsistent. Not enough to ground the fighter, not enough to trigger official alarms, enough to create uncertainty, and uncertainty in combat can be deadly. The challenge was finding a cause. The P-38 was a complex machine. Control inputs traveled through an intricate network of cables, pulleys, bell cranks, hinges, and linkages before reaching the control surfaces. Even minor wear could influence how the aircraft felt. The mechanic began inspecting components more carefully. He checked cable tensions. He examined pulley systems. He inspected attachment points. Nothing obvious appeared. No broken parts. No major defects. No smoking gun. Official engineering reports from the United States occasionally arrived through military channels, but those reports were often weeks or months old by the time they reached remote Pacific bases. Engineers back home studied performance data. They analyzed maintenance records. They reviewed pilot feedback, but they were separated from the daily reality of combat operations. The mechanic wasn't. Every damaged aircraft rolled directly in front of him. Every pilot complaint reached his ears. Every maintenance challenge landed on his workbench. That proximity created an advantage. He could observe things in real time. One afternoon, after another long series of inspections, he noticed something interesting. Aircraft that felt better in flight often shared small differences in control system wear patterns. The observation wasn't conclusive, but it was enough to spark an idea. The idea wasn't sophisticated. In fact, that was part of the problem. Sometimes simple solutions appear too simple. The mechanic began wondering whether a slight change in tension or control linkage behavior might influence how the aircraft responded during specific maneuvers. Not a redesign, not a major modification, just a subtle adjustment, a tiny change. The kind of change engineers might never notice from thousands of miles away. The kind of change a mechanic notices because he's physically touching the machine every day. The idea lingered in his mind for days, then weeks. He replayed pilot comments, compared inspection notes, examined aircraft repeatedly. Gradually, the theory became harder to ignore. If he was right, a minor alteration could reduce the inconsistency pilots were describing. If he was wrong, nothing would change. There was only one way to find out. Testing an idea during wartime wasn't as simple as conducting a laboratory experiment. Everything carried risk. Aircraft were valuable. Pilots were irreplaceable. Mistakes had consequences. Yet frontline maintenance crews improvised constantly because circumstances demanded it. Parts shortages required creativity. Combat damage required adaptation. Innovation often happened because there was no alternative. The mechanic finally decided to act. He gathered a few components, studied the linkage system once more, then considered a modification so small that most people would overlook it completely. A piece of wire, not an expensive component, not a factory upgrade, just wire. When he described the concept to others, the reaction was predictable. Some laughed, others dismissed it immediately. A few questioned whether it could possibly make any difference at all. After all, how could something so insignificant affect one of the most advanced fighters in the Pacific? The skepticism was understandable. The idea sounded absurd, which was exactly why nobody had tried it before. Then he decided to install it anyway. And what happened next surprised everyone. Then he tried a modification that sounded absurd. Nothing about the aircraft looked different. Everything felt different. That was the strange part. When the mechanic finished the modification, nobody walking past the P-38 would have noticed anything unusual. The twin Allison engines were still there. The twin booms were unchanged. The armament remained exactly the same. The aircraft weighed virtually the same as it had the day before. No new equipment appeared in maintenance logs. No major components had been replaced. Yet hidden within the aircraft's control system was a small adjustment built around a simple wire linkage, PSI-TE. To understand why the idea seemed ridiculous, it's important to understand how aircraft maintenance culture worked during the war. Most mechanics respected field improvisation. They had to. Pacific operations demanded creativity, but there was a difference between repairing an aircraft and modifying one. Repairs restored an aircraft to its intended condition. Modifications risked introducing new problems. Nobody wanted to be responsible for making a fighter less safe, especially not a fighter carrying a pilot hundreds of miles over open ocean. That was why many mechanics reacted skeptically when they heard the proposal. A wire? That was the solution? Not a redesigned control surface, not a factory-issued update, not a new engineering directive, just a small change involving a piece of wire and the behavior of a control linkage, CIT. To some, the idea sounded almost insulting. The P-38 represented one of the most sophisticated aircraft in American service. Lockheed engineers had spent years designing it. Thousands of workers had manufactured its components. Countless hours had gone into testing. And now someone was suggesting that a simple field adjustment might improve the way it handled. The mechanic understood the skepticism. He shared part of it himself. That was why he approached the modification cautiously. First came inspections, then measurements, then more inspections. The goal wasn't to reinvent the aircraft. The goal was to remove a subtle inconsistency that seemed to appear under certain flight conditions. During routine maintenance intervals, control systems were already checked for wear, cable tension, pulley alignment, and freedom of movement. The mechanic focused his attention on those areas. He looked for small amounts of slack, tiny delays between pilot input and control response. Minor inconsistencies that might seem insignificant on the ground but become noticeable during aggressive maneuvering. In combat, fractions of a second matter. A control surface doesn't need to fail to create problems. It only needs to respond slightly differently than expected. The modification was intended to reduce that uncertainty. The wire created additional tension within part of the linkage system, helping maintain more consistent behavior during specific maneuvering loads, sight. On paper, the change seemed almost laughably small. A few inches here, a slight adjustment there. Nothing dramatic. Certainly nothing that looked capable of influencing aerial combat. Still, the mechanic completed the installation. Then came the difficult part. Testing it. Combat aircraft weren't laboratory equipment. You couldn't simply take them apart and experiment endlessly. Every airplane was needed. Every flying hour mattered. Yet before risking a combat mission, somebody needed to determine whether the modification changed anything at all. The first test flight was deliberately conservative. The pilot knew only that maintenance personnel wanted feedback. Nothing more. No promises, no claims, no expectations. The aircraft lifted from the coral runway shortly after sunrise. Conditions were typical for the South Pacific. Warm air, high humidity, scattered cloud cover, visibility stretching for miles over open water. The pilot climbed through several thousand feet and began evaluating handling characteristics. Gentle turns first, then steeper banks, then more aggressive maneuvers. Nothing unusual, at least not initially. The aircraft remained stable, predictable, normal. The pilot continued the evaluation. Speeds increased. Control inputs became sharper. The maneuvering grew more demanding. That was when he noticed it. Not a dramatic improvement, not a sudden transformation, just a feeling, a subtle sensation, that the aircraft responded more cleanly than before. The controls seemed more connected, more immediate. The delay he occasionally sensed during certain maneuvers appeared reduced. The pilot completed additional turns, then repeated them again. By the time he returned to the airfield, he wasn't entirely sure what had changed, but he was sure something had. The mechanic listened carefully. What exactly did it feel like? Where? At what speeds? During which maneuvers? The answers were frustratingly vague. Pilots often describe aircraft the same way drivers describe cars. They know when something feels different. Explaining why is harder. Yet over the following days, more test flights occurred. Each generated similar feedback. Nothing revolutionary. Nothing dramatic. Just consistent reports. The aircraft felt smoother, more predictable, more responsive. Most importantly, pilots appeared to gain confidence in the machine. Confidence matters, especially in combat aviation. A pilot who trusts his aircraft reacts faster. He commits to maneuvers sooner. He wastes less mental energy questioning the machine beneath him. The modification still had critics. Some mechanics argued that the improvement was psychological. Others suggested pilots simply expected better performance after hearing rumors about the change. A few dismissed the entire idea. If the modification worked, where was the proof? The criticism was fair. Anecdotes aren't data. Test flights aren't combat. The Pacific had a way of exposing weaknesses that controlled evaluations never revealed. An aircraft might feel excellent during practice, then behave differently under stress. Combat creates conditions impossible to reproduce on the ground. Adrenaline changes perception. Enemy aircraft change decision-making. Extreme maneuvers reveal flaws hidden during routine operations. The mechanic understood all of that. He never claimed victory. He never declared the problem solved. Instead, he kept gathering observations. More inspections, more pilot feedback, more comparisons. Gradually, a pattern emerged. Aircraft fitted with the modification repeatedly generated similar comments. Not from one pilot, not from two, from several. Independent observations began pointing in the same direction. The wire wasn't creating extra horsepower, it wasn't increasing speed, it wasn't changing armament. What it appeared to be doing was far more subtle. It was helping pilots extract more of the performance already built into the aircraft. That distinction mattered because battlefield advantages are often misunderstood. Sometimes victory comes from adding capability. Other times it comes from removing limitations. The mechanic believed the wire belonged in the second category. If he was right, the Lightning had always possessed the potential. Pilots simply hadn't been accessing it consistently. There was only one way to know for sure. The next stage wouldn't happen over a test range. It wouldn't happen above a friendly airfield. It wouldn't happen during a maintenance inspection. It would happen where every theory eventually faced judgment. In combat. The real test would come in combat. For the first time, the Zero pilot was reacting instead of dictating. That was the difference. Not speed, not firepower, not a revolutionary new technology. The P-38 had always possessed those advantages. What changed was the pilot's ability to use them. The first real test arrived several weeks later. Shortly after dawn, a squadron of Lightnings prepared for another long-range patrol mission over the Southwest Pacific. The weather forecast was typical for the region: scattered clouds, light winds, visibility exceeding 20 miles. Temperatures already climbing despite the early hour. Ground crews moved between aircraft conducting final inspections. Fuel tanks were topped off. Weapons checked. Control surfaces tested one last time. Pilots completed briefings while maintenance crews watched from the edge of the runway. The mechanic stood among them. He didn't say much. There wasn't much to say. The aircraft would either perform differently or they wouldn't. Combat would decide. One after another, the twin-engine fighters rolled forward. Engines roared. Propellers blurred. The Lightnings accelerated down the coral runway before lifting into the humid Pacific air. Within minutes, they were climbing toward operational altitude. 10,000 feet, 15,000, 20,000. The formation settled into a steady cruise. Beneath them stretched hundreds of miles of ocean. Above them hung scattered cloud layers illuminated by the morning sun. Hours passed. Navigation updates flowed across the radios. Fuel calculations continued. Pilots scanned the horizon. Most missions ended without contact. This one didn't. Shortly after noon, one of the formation leaders spotted movement ahead. Tiny dark shapes. High, fast closing. The radio crackled immediately. Bandits! 11 o'clock high! Every pilot's attention shifted instantly. The patrol mission ended. Combat began. The Japanese aircraft held the altitude advantage, approximately 24,000 feet, several thousand feet above the approaching Americans. The formation identified them quickly. Zeros, the most familiar opponent in the Pacific, the Japanese fighters descended aggressively. Their intention was obvious: use altitude, build speed, force the Americans to react. For years, similar encounters had followed predictable patterns. The Japanese dictated the opening engagement. American pilots responded. The Zero's maneuverability often allowed its pilots to control the geometry of the fight. Not always, but often enough. This time, something felt different. The first merge occurred at speeds approaching 300 miles per hour. Aircraft flashed past each other. Pilots pulled hard into climbing turns. Contrails briefly appeared before dissolving into the humid air. The sky erupted into dozens of independent engagements. Within seconds, formations disappeared. Individual pilots found themselves fighting individual battles. One Lightning pilot locked onto a Zero, attempting a familiar maneuver. The Japanese fighter entered a tightening left-hand turn. The move had worked countless times before. Force the heavier aircraft into a turning contest. Watch it lose energy. Exploit the advantage. The American pilot followed. Normally, this was the point where frustration began. The aircraft might hesitate slightly. The positioning would deteriorate. The Zero would gradually gain the advantage. Instead, the distance remained surprisingly stable. 800 yards? 700? 600. The pilot adjusted throttle and bank angle. The aircraft responded smoothly. Not magically, simply predictably. That predictability mattered. Every maneuver in aerial combat involves trade-offs. Pilots exchange altitude for speed, speed for turning performance, position for opportunity. The better a pilot understands his aircraft, the more efficiently he can make those exchanges. The modified Lightning wasn't violating the laws of physics. It wasn't suddenly turning like a zero. It didn't need to. It only needed to stop wasting performance. The pilot realized he was maintaining energy more effectively throughout the maneuver. The aircraft felt cleaner, more cooperative. Instead of constantly correcting small deviations, he could focus on the fight itself. That freed mental bandwidth, and mental bandwidth wins engagements. The Zero tightened its turn. The Lightning remained behind it. The Japanese pilot rolled into another maneuver. The American followed. The gap narrowed. 500 yards, 400, 300. The radio came alive. "He's still in front of me." The voice sounded surprised, almost confused. Other pilots reported similar experiences. Not victories, not miracles, just opportunities. Opportunities they hadn't always enjoyed before. The engagement continued for several minutes. Aircraft climbed and descended through layers of broken cloud. Altitudes fluctuated between 12,000 and 22,000 feet. Speeds varied from near-stall margins during tight maneuvering to more than 350 miles per hour during diving recoveries. The conditions were chaotic, exactly the kind of environment where small handling improvements become meaningful. One pilot later described the difference in simple terms. He spent less time fighting the aircraft, more time fighting the enemy. That wasn't a technical explanation, but it may have been the most accurate one. As the battle unfolded, another important effect emerged. Confidence. Pilots began trusting the aircraft's response. That trust encouraged decisive action. Instead of hesitating during transitions between maneuvers, they committed. Instead of second-guessing control inputs, they focused on positioning. The cumulative effect was subtle but significant. Each decision occurred a fraction of a second faster. Each maneuver became slightly more efficient. Those fractions accumulated. Aerial combat often turns on tiny margins. The Japanese pilots noticed the change too. Not the modification itself, the behavior. The Americans weren't reacting the way they expected. Traditional assumptions weren't producing traditional results. Several Zeros attempted repeated direction reversals. Others climbed aggressively. Some tried to drag the fight lower. Yet the Lightnings consistently maintained better positioning than expected. Not perfectly, not every time, but often enough to attract attention. One engagement near the edge of the battle illustrated the difference clearly. A Zero attempted to force an overshoot by abruptly tightening a descending turn. The maneuver had trapped many opponents before. The American pilot anticipated it. The Lightning responded cleanly. Instead of sliding wide, the aircraft stayed inside the expected line. The pilot maintained visual contact, maintained energy, maintained pressure. Moments later, the Japanese fighter broke away entirely. For the first time in the encounter, it was attempting to escape rather than dominate. That moment stayed with several participants because it represented a reversal of expectations. The Zero remained dangerous. The pilot remained skilled. Nothing about the engagement was easy, yet the initiative had shifted. The Japanese pilot was reacting. The American was dictating. By the time the surviving aircraft returned to base later that day, maintenance crews were waiting. Pilots climbed from cockpits exhausted, dehydrated, and covered in sweat. The mission had lasted more than 7 hours. Most of that time had been spent crossing open ocean. Only minutes had been spent fighting, yet those minutes generated endless discussion. The reports sounded familiar. The aircraft felt better. The controls felt more responsive. Positioning felt easier to maintain. Nobody claimed the modification transformed the P-38 into a zero killer. That wasn't the point. The point was that pilots increasingly felt able to exploit strengths the aircraft already possessed: speed, power, energy retention, firepower. The wire hadn't created those advantages. It had simply helped pilots access them more effectively. For the mechanic, the feedback was encouraging. For skeptical observers, it was becoming harder to dismiss, and that was where an unexpected problem emerged. Success attracts attention. Attention attracts scrutiny, and scrutiny was about to become a problem. But success created a new problem. The hardest battle wasn't against Japan. It was against disbelief. Success has a strange effect inside large organizations. Everyone wants results. Not everyone trusts where those results come from. The reports arriving from the Pacific should have been encouraging. Pilots were describing improved handling. Squadrons were reporting more confidence in specific aircraft. Maintenance crews observed consistent feedback patterns. The modification appeared to be working. Instead of celebration, however, the reports triggered skepticism. Part of that skepticism was reasonable. Military aviation depends on evidence. Aircraft modifications cannot be approved simply because someone feels they work. Lives depend on verification. Combat reports are notoriously unreliable. Pilots misjudge distances, misremember speeds, misidentify aircraft, confuse causes and effects. A fighter pilot might swear a modification improved performance when the real explanation was better weather, better positioning, or simply luck. Senior officers understood this. Engineers understood it even more. From their perspective, extraordinary claims demanded extraordinary proof. The problem was that nobody could easily explain why such a simple modification seemed effective. That alone made people suspicious. The war had created one of the largest technical organizations in history. Factories employed thousands. Research facilities tested countless components. Engineers analyzed mountains of data. Every major aircraft system underwent years of development before reaching combat units. Yet now reports suggested that an enlisted mechanic on a remote Pacific airfield might have discovered something that had escaped official attention. For some people, that possibility was difficult to accept, not because they were arrogant, because it challenged assumptions. Large organizations naturally assume expertise flows downward. Designers create solutions. Field personnel implement them. The idea that valuable innovation might flow in the opposite direction felt uncomfortable, especially during wartime. Questions began appearing in official correspondence. Had the modification actually changed aircraft behavior, or were pilots imagining differences because they expected improvements? The debate quickly centered on a concept that modern researchers would recognize immediately: placebo effects. Even in aviation, expectations can influence perception. If pilots believe an aircraft has been improved, they may unconsciously interpret normal performance as exceptional performance. Several officers suspected exactly that. The argument seemed logical. Pilots heard rumors about the modification. They expected better handling. They reported better handling. Case closed. Except the situation wasn't that simple, because many of the positive reports originated before pilots fully understood what had been changed. Some didn't even know a modification existed. Others learned about it only after describing differences they had already experienced. That complicated the placebo explanation. Still, skepticism remained. Military bureaucracy moves deliberately for a reason. Imagine approving a modification across hundreds of aircraft based on anecdotal evidence. If the change later created an unexpected failure, the consequences could be catastrophic. No commander wanted that responsibility. No engineer wanted that responsibility either. As a result, the reports entered a familiar wartime process. Paperwork, evaluations, requests for clarification, requests for additional testing, requests for more data. The Pacific might have been moving at combat speed. Administration moved at administrative speed. Every observation required documentation. Every recommendation required review. Every review generated additional questions. Messages crossed thousands of miles between combat zones and headquarters. Weeks passed, sometimes months. Meanwhile, combat operations continued. Pilots kept flying, mechanics kept working, and the debate continued. The contrast became increasingly obvious. The front line viewed the problem through experience. Headquarters viewed it through procedure. Neither perspective was entirely wrong. The mechanic represented practical knowledge. He observed aircraft daily. He listened to pilots. He inspected worn components. He recognized patterns. The engineers represented systematic knowledge. They needed measurable evidence. Repeatable results. Technical explanations. The challenge was bridging the gap between those worlds. History often celebrates dramatic innovations. The revolutionary engine, the breakthrough radar system, the new aircraft design. But many wartime improvements were smaller, messier, harder to prove. They emerged through observation rather than theory. One Lightning pilot locked onto a Zero attempting a familiar maneuver. The Japanese fighter entered a tightening left-hand turn. The move had worked countless times before. Force the heavier aircraft into a turning contest. Watch it lose energy. Exploit the advantage. The American pilot followed. Normally, this was the point where frustration began. The aircraft might hesitate slightly. The positioning would deteriorate. The Zero would gradually gain the advantage. Instead, the distance remained surprisingly stable. 800 yards? 700? 600. The pilot adjusted throttle and bank angle. The aircraft responded smoothly. Not magically, simply predictably. That predictability mattered. Every maneuver in aerial combat involves trade-offs. Pilots exchange altitude for speed, speed for turning performance, position for opportunity. The better a pilot understands his aircraft, the more efficiently he can make those exchanges. The modified Lightning wasn't violating the laws of physics. It wasn't suddenly turning like a Zero. It didn't need to. It only needed to stop wasting performance. The pilot realized he was maintaining energy more effectively throughout the maneuver. The aircraft felt cleaner, more cooperative. Instead of constantly correcting small deviations, he could focus on the fight itself. That freed mental bandwidth, and mental bandwidth wins engagements. The Zero tightened its turn. The Lightning remained behind it. The Japanese pilot rolled into another maneuver. The American followed. The gap narrowed. 500 yards, 400, 300. The radio came alive. "He's still in front of me." The voice sounded surprised, almost confused. Other pilots reported similar experiences. Not victories, not miracles, just opportunities. Opportunities they hadn't always enjoyed before. The engagement continued for several minutes. Aircraft climbed and descended through layers of broken cloud. Altitudes fluctuated between 12,000 and 22,000 feet. Speeds varied from near stall margins during tight maneuvering to more than 350 miles per hour during diving recoveries. The conditions were chaotic, exactly the kind of environment where small handling improvements become meaningful. One pilot later described the difference in simple terms. He spent less time fighting the aircraft, more time fighting the enemy. That wasn't a technical explanation, but it may have been the most accurate one. As the battle unfolded, another important effect emerged: confidence. Pilots began trusting the aircraft's response. That trust encouraged decisive action. Instead of hesitating during transitions between maneuvers, they committed. Instead of second-guessing control inputs, they focused on positioning. The cumulative effect was subtle but significant. Each decision occurred a fraction of a second faster. Each maneuver became slightly more efficient. Those fractions accumulated. Aerial combat often turns on tiny margins. The Japanese pilots noticed the change too. Not the modification itself, the behavior. The Americans weren't reacting the way they expected. Traditional assumptions weren't producing traditional results. Several Zeros attempted repeated direction reversals. Others climbed aggressively. Some tried to drag the fight lower. Yet the Lightnings consistently maintained better positioning than expected. Not perfectly, not every time, but often enough to attract attention. One engagement near the edge of the battle illustrated the difference clearly. A Zero attempted to force an overshoot by abruptly tightening a descending turn. The maneuver had trapped many opponents before. The American pilot anticipated it. The Lightning responded cleanly. Instead of sliding wide, the aircraft stayed inside the expected line. The pilot maintained visual contact, maintained energy, maintained pressure. Moments later, the Japanese fighter broke away entirely. For the first time in the encounter, it was attempting to escape rather than dominate. That moment stayed with several participants because it represented a reversal of expectations. The Zero remained dangerous. The pilot remained skilled. Nothing about the engagement was easy, yet the initiative had shifted. The Japanese pilot was reacting. The American was dictating. By the time the surviving aircraft returned to base later that day, maintenance crews were waiting. Pilots climbed from cockpits exhausted, dehydrated, and covered in sweat. The mission had lasted more than 7 hours. Most of that time had been spent crossing open ocean. Only minutes had been spent fighting. Yet those minutes generated endless discussion. The reports sounded familiar. The aircraft felt better. The controls felt more responsive. Positioning felt easier to maintain. Nobody claimed the modification transformed the P-38 into a Zero killer. That wasn't the point. The point was that pilots increasingly felt able to exploit strengths the aircraft already possessed: speed, power, energy retention, firepower. The wire hadn't created those advantages. It had simply helped pilots access them more effectively. For the mechanic, the feedback was encouraging. For skeptical observers, it was becoming harder to dismiss. And that was where an unexpected problem emerged. Success attracts attention. Attention attracts scrutiny. And scrutiny was about to become a problem. But success created a new problem. The hardest battle wasn't against Japan. It was against disbelief. Success has a strange effect inside large organizations. Everyone wants results. Not everyone trusts where those results come from. The reports arriving from the Pacific should have been encouraging. Pilots were describing improved handling. Squadrons were reporting more confidence in specific aircraft. Maintenance crews observed consistent feedback patterns. The modification appeared to be working. Instead of celebration, however, the reports triggered skepticism. Part of that skepticism was reasonable. Military aviation depends on evidence. Aircraft modifications cannot be approved simply because someone feels they work. Lives depend on verification. Combat reports are notoriously unreliable. Pilots misjudge distances, misremember speeds, misidentify aircraft, confuse causes and effects. A fighter pilot might swear a modification improved performance when the real explanation was better weather, better positioning, or simply luck. Senior officers understood this. Engineers understood it even more. From their perspective, extraordinary claims demanded extraordinary proof. The problem was that nobody could easily explain why such a simple modification seemed effective. That alone made people suspicious. The war had created one of the largest technical organizations in history. Factories employed thousands. Research facilities tested countless components. Engineers analyzed mountains of data. Every major aircraft system underwent years of development before reaching combat units. Yet now reports suggested that an enlisted mechanic on a remote Pacific airfield might have discovered something that had escaped official attention. For some people, that possibility was difficult to accept, not because they were arrogant, because it challenged assumptions. Large organizations naturally assume expertise flows downward. Designers create solutions. Field personnel implement them. The idea that valuable innovation might flow in the opposite direction felt uncomfortable, especially during wartime. Questions began appearing in official correspondence. Had the modification actually changed aircraft behavior, or were pilots imagining differences because they expected improvements? The debate quickly centered on a concept that modern researchers would recognize immediately: placebo effects. Even in aviation, expectations can influence perception. If pilots believe an aircraft has been improved, they may unconsciously interpret normal performance as exceptional performance. Several officers suspected exactly that. The argument seemed logical. Pilots heard rumors about the modification. They expected better handling. They reported better handling. Case closed. Except the situation wasn't that simple, because many of the positive reports originated before pilots fully understood what had been changed. Some didn't even know a modification existed. Others learned about it only after describing differences they had already experienced. That complicated the placebo explanation. Still, skepticism remained. Military bureaucracy moves deliberately for a reason. Imagine approving a modification across hundreds of aircraft based on anecdotal evidence. If the change later created an unexpected failure, the consequences could be catastrophic. No commander wanted that responsibility. No engineer wanted that responsibility either. As a result, the reports entered a familiar wartime process. Paperwork, evaluations, requests for clarification, requests for additional testing, requests for more data. The Pacific might have been moving at combat speed. Administration moved at administrative speed. Every observation required documentation. Every recommendation required review. Every review generated additional questions. Messages crossed thousands of miles between combat zones and headquarters. Weeks passed, sometimes months. Meanwhile, combat operations continued. Pilots kept flying, mechanics kept working, and the debate continued. The contrast became increasingly obvious. The front line viewed the problem through experience. Headquarters viewed it through procedure. Neither perspective was entirely wrong. The mechanic represented practical knowledge. He observed aircraft daily. He listened to pilots. He inspected worn components. He recognized patterns. The engineers represented systematic knowledge. They needed measurable evidence. Repeatable results. Technical explanations. The challenge was bridging the gap between those worlds. History often celebrates dramatic innovations. The revolutionary engine, the breakthrough radar system, the new aircraft design. But many wartime improvements were smaller, messier, harder to prove. They emerged through observation rather than theory. They lived in the space between engineering and experience. That was exactly where this modification existed. The mechanic couldn't produce complex aerodynamic calculations. He didn't have access to advanced testing facilities. What he had was evidence from the field, evidence that became increasingly difficult to ignore. Pilots continued requesting aircraft equipped with the modification. That fact alone attracted attention. Fighter pilots are practical people. They don't care where a solution comes from. They care whether it works. If a specific aircraft consistently felt better during combat, pilots noticed. And when enough pilots notice the same thing, commanders start paying attention. Still, resistance remained. Some officers worried about setting a dangerous precedent. What would happen if every squadron began inventing its own modifications? How would standardization survive? How would maintenance procedures remain consistent? How would engineers evaluate dozens of competing field innovations? The concerns were legitimate. War requires adaptation. It also requires discipline. Finding the balance is difficult. For a time, the debate seemed destined to remain unresolved. Supporters pointed to combat experiences. Critics pointed to insufficient evidence. Neither side could fully convince the other. Then something began changing. Not opinions, numbers. The war generated enormous amounts of information. Maintenance logs, pilot reports, inspection records, mission summaries, performance evaluations. Individually, those documents revealed very little. Collectively, they told stories. And slowly, one particular story started emerging. Patterns appeared across multiple aircraft, across multiple pilots, across multiple missions. The same observations repeated again and again. The kind of repetition that transforms anecdotes into evidence. The kind of repetition that forces organizations to pay attention, because opinions can be argued with, stories can be dismissed, feelings can be questioned. Data is much harder to ignore. Then the data started arriving. The evidence became impossible to ignore. For months, the debate had revolved around opinions. Pilots believed the modification worked. Some officers remained skeptical. Engineers wanted proof. Now the war was beginning to provide it, not through a single dramatic report, not through one extraordinary combat mission, through repetition, the same story appearing again and again across hundreds of pages of paperwork. That was how most military truths emerged, not as revelations, as patterns. The first signs appeared in squadron maintenance records, aircraft fitted. With the modification, continued generating positive pilot feedback at unusually consistent rates, sight. Different pilots, different missions, different weather conditions, yet remarkably similar observations. Words such as smoother, more predictable, and more responsive appeared repeatedly in post-mission debriefs. Individually, those comments meant very little. Collectively, they began attracting attention. One report can be dismissed. 50 reports become harder to ignore. 100 become impossible. The maintenance personnel noticed something else. Pilots were beginning to request specific aircraft. That may not sound significant. In reality, it was. Fighter pilots are notoriously selective. When your life depends on a machine, preferences matter. Some pilots preferred certain engines. Others preferred specific gun harmonization patterns. Many developed trust in particular aircraft. Now, another preference was emerging. Whenever possible, pilots requested aircraft known to carry the modification. Officially, few people admitted why. Unofficially, everybody understood. They believed those aircraft performed better. The requests became frequent enough that commanders began asking questions. What exactly was happening? Why were experienced pilots gravitating toward the same aircraft? Were they imagining differences, or was something genuinely changing performance? To answer those questions, more formal evaluations began. The process wasn't glamorous. No dramatic testing range, no secret facility, no cinematic moment where a senior officer suddenly changes his mind. Instead, investigators did what investigators always do. They collected data, mission reports, maintenance records, pilot questionnaires, inspection notes, performance observations. Then they compared them. The numbers weren't perfect. Combat data never is. But certain trends began appearing with surprising consistency. Aircraft fitted with the modification generated fewer complaints, related to the handling characteristics that had originally sparked concern, cite. Pilots reported greater confidence during aggressive maneuvering. Maintenance crews observed more uniform control system behavior during inspections. Perhaps most importantly, positive reports originated from pilots with widely different experience levels. Veterans noticed it, new pilots noticed it, test pilots noticed it. That broad agreement carried weight. Experienced aviators often disagree about everything. When they start agreeing, people pay attention. The evaluations expanded. Soon, investigators examined sortie records. The Pacific War generated enormous numbers of flights, escort missions, interceptions, reconnaissance support, long-range patrols. Every sortie produced information. Thousands of hours accumulated. Thousands more observations followed. As analysts reviewed the records, another pattern emerged. The modification wasn't turning the P-38 into a completely different aircraft. That distinction remained critical. The Lightning still behaved like a Lightning. It still possessed the same strengths, the same limitations, the same aerodynamic realities. The wire wasn't creating performance. It was helping unlock performance that already existed. That made the results easier to understand. Some innovations add capability. Others reduce inefficiency. This appeared to belong firmly in the second category. Imagine a skilled marksman using a rifle with a slightly inconsistent trigger. The rifle may still be accurate. The shooter may still perform well. But remove the inconsistency and performance often improves immediately. Not because the shooter changed, because the obstacle disappeared. That was increasingly how evaluators described the modification. It wasn't creating miracles, it was removing friction. As the evidence accumulated, even some skeptics began softening their positions. Not everyone. There were still objections. Some engineers questioned whether the observed improvements could be measured precisely. Others worried that maintenance variations between individual aircraft complicated the analysis. Those concerns remained valid, but the discussion itself was changing. Earlier debates focused on whether the modification worked at all. Now debates focused on exactly why it worked. That shift mattered. It represented progress. The burden of proof had begun moving. Supporters no longer needed to convince everyone something was happening. The evidence had largely settled that question. Now the challenge involved understanding the mechanism. Meanwhile, combat operations continued, and combat provided perhaps the strongest evidence of all. Pilots trusted the modification because they trusted results, not statistics, not reports. Results. A pilot who survives an engagement remembers what happened. A pilot who gains a positional advantage notices. A pilot who feels more confident maneuvering against an opponent notices even more. The stories continued spreading through squadrons. Sometimes officially, often unofficially, air crews talk, maintenance crews talk. Rumors travel quickly through military organizations. Soon, personnel arriving from other units began hearing about the modification before they ever saw it. Some dismissed the stories as exaggeration. Others became curious. A few actively sought opportunities to evaluate the aircraft themselves. The cycle repeated. They flew. They compared. They reported. And more often than not, the feedback sounded familiar. The aircraft felt different. Subtly. Consistently. Positively. At headquarters, stacks of documentation continued growing. Sortie counts increased. Inspection findings accumulated. Pilot evaluations multiplied. The picture became clearer with every passing month. What began as an unofficial experiment was evolving into accepted practice. That transformation did not happen overnight. Military organizations rarely change quickly, especially during wartime. Procedures exist for a reason. Standards exist for a reason. Approvals exist for a reason. Yet eventually enough evidence accumulates that resistance becomes harder than acceptance. The modification reached that point. The numbers no longer supported dismissal. The reports no longer looked isolated. The observations no longer appeared anecdotal. Too many people were seeing the same thing. Too many documents pointed in the same direction. Too many combat experiences reinforced the conclusion. The evidence had achieved something rare. It had crossed the threshold from possibility to credibility. And once credibility arrives, institutional change often follows. Gradually, the modification moved through official channels. Maintenance guidance adapted. Recommendations expanded. Acceptance spread. What had begun as a mechanics field improvisation now possessed something every innovation needs to survive. Validation. The irony was impossible to miss. An idea that initially sounded ridiculous had survived scrutiny. Not because of rank, not because of authority, because of evidence. The war had subjected the modification to the harshest testing environment imaginable. Thousands of miles of ocean, hundreds of missions, countless maintenance inspections, real combat, real consequences, and it had endured. The Lightning remained the same aircraft. The Pacific remained the same battlefield. Yet one small adjustment had quietly improved the relationship between pilot and machine. That improvement mattered, not because it changed history by itself, but because wars are often influenced by countless small advantages accumulating over time. A few extra seconds of control, a little more confidence, a little less uncertainty, enough to matter, enough to survive, enough to win. Yet despite all the reports, all the evaluations, and all the growing acceptance, one thing never changed. The modification became known. The mechanic did not. Yet the mechanic's name would not become famous. History remembers aces. It often forgets who kept them alive. That isn't a criticism of history. It's simply how stories tend to work. People remember dramatic moments. The fighter pilot who wins the aerial duel, the commander who leads the offensive, the general whose name appears in newspapers. Those stories are easier to tell. They have faces. They have victories. They have endings. The people who maintain machines rarely receive the same attention. Yet war has always depended on them. Long before a pilot enters combat, someone else has already spent hours preparing the aircraft. Before a gun fires, someone inspected it. Before an engine starts, someone repaired it. Before a mission succeeds, someone solved a problem nobody else noticed. The mechanic behind the wire modification belonged to that tradition. His contribution mattered not because it was dramatic. It mattered because it represented something larger, a truth repeated throughout military history. Innovation does not always come from the top. Sometimes it comes from the people closest to the problem. That idea makes some organizations uncomfortable. It always has. Modern institutions depend on expertise. Aircraft are designed by engineers. Weapons are developed by specialists. Procedures are created through testing and analysis. None of that is wrong. In fact, it is essential. The P-38 itself was proof. The aircraft existed because of thousands of skilled designers, engineers, manufacturers, inspectors, and technicians. Without them, there would have been no lightning to improve. Yet expertise has limits. No engineer, regardless of talent, can fully predict every condition a machine will encounter in war. The Pacific demonstrated that reality every day. Heat, humidity, salt air, coral dust, long-range operations, pilot fatigue, combat stress. Each factor introduced variables difficult to reproduce in controlled environments. A machine that performs perfectly during testing may behave differently after months of combat operations. That is where practical experience becomes valuable. The mechanic wasn't competing with engineers. He was complementing them. His insight emerged because he occupied a different position within the system. He saw things they could not. He heard the conversations, observed the patterns, touched the aircraft every day. The contrast between engineering and experience often appears throughout wartime innovation. Engineers create systems. Operators reveal weaknesses. Maintainers identify recurring problems. Together, they improve the machine. The most successful military organizations learn to listen to all three. The least successful assume valuable ideas can originate only from one direction. History provides countless examples. Tank crews improvising battlefield repairs. Armorers modifying equipment based on combat experience. Naval personnel developing practical solutions far from shipyards. Ground crews adapting aircraft for conditions designers never anticipated. Most of those innovations never become famous. Many disappear entirely from public memory. Not because they lacked importance, because they lacked visibility. The people responsible rarely wrote memoirs. Few journalists interviewed them. Even official histories often focused elsewhere. As a result, countless contributions vanished into maintenance logs, technical reports, and forgotten archives. The wire modification fits comfortably within that pattern. Whether viewed as a mechanical adjustment, a maintenance innovation, or a lesson in battlefield adaptation, its significance extends beyond the P-38 itself. The story isn't really about a wire, and it isn't even entirely about an aircraft. It's about observation, patience, curiosity, the willingness to question assumptions. Most people accepted that the P-38 behaved a certain way. Pilots adapted, commanders adapted. The war continued. The mechanic did something slightly different. He paid attention, then he asked a question. What if the problem wasn't inevitable? That question changed everything. Not immediately, not dramatically. Gradually. The way meaningful improvements often happen. A small observation led to a small experiment. The experiment produced small results. Those results accumulated. Eventually, they became impossible to ignore. That sequence appears repeatedly throughout history, rarely glamorous, frequently important. Another lesson emerges from the story as well. Victory is often portrayed as the result of grand strategy. Massive production numbers, powerful weapons, brilliant leadership. All of those factors matter, yet wars are also shaped by details. Tiny details. Details so small they barely attract attention at the time. A maintenance shortcut that saves hours. A redesigned component that improves reliability. A procedural change that reduces mistakes. A wire that improves control response. Individually, such changes appear insignificant. Collectively, they influence outcomes. One aircraft performs slightly better. One pilot survives. One mission succeeds. One squadron gains confidence. The effects spread outward. Not enough to rewrite history alone, enough to become part of it. That perspective helps explain why so many military veterans speak respectfully about maintenance personnel. Pilots understood something civilians sometimes overlook. Flying the aircraft was only part of the job. Keeping it operational required an entire team. Every successful mission represented collective effort. The pilot received the credit because the pilot occupied the cockpit. But the cockpit was never occupied alone. Invisible hands traveled with every flight. The mechanics who tightened bolts, the armorers who loaded ammunition, the specialists who inspected engines, the technicians who solved problems before they became disasters. They all contributed. Most remained anonymous. The wartime record contains thousands of such individuals, people whose names disappeared while their work endured. The mechanic behind the wire modification may never achieve the recognition of a famous ace. He may never appear in major history books. Many viewers may forget his name even before this story ends. Yet in some ways, that anonymity makes the lesson stronger, because the story stops being about one man. It becomes about all of them. The maintainers, the armorers, the technicians, the problem solvers, the people working long hours in difficult conditions while others received the headlines. History remembers victories. History remembers commanders. History remembers aces. But behind nearly every famous success stands a much larger group whose contributions remain hidden. The wire became a symbol of that reality, a reminder that innovation often arrives quietly, a reminder that expertise exists at every level, and a reminder that some of the most important changes begin with someone paying attention when everyone else stops looking. One final lesson remains. A few inches of wire changed what happened in the sky. At first, that sounds impossible. When we think about military history, we tend to think in large numbers. Thousands of aircraft, millions of rounds of ammunition, entire fleets crossing oceans, massive industrial programs producing machines on a scale the world had never seen before. The Second World War was certainly a story of scale. Factories mattered, resources mattered, technology mattered. But scale is only part of the story. The other part lives in details. Small details. The kinds of details most people overlook. A mechanic notices an unusual wear pattern. A pilot mentions a recurring problem. A maintainer asks a question nobody else is asking. Those moments rarely make headlines, yet they often become the starting point for meaningful change. That is why this story matters. Not because a wire alone transformed the Pacific Air War. It didn't. Not because one modification suddenly made the P-38 unbeatable. It didn't do that either. The real lesson is much more interesting. Progress often begins with observation. The mechanic didn't possess unlimited resources. He didn't command a research laboratory. He didn't have authority over aircraft design. What he had was curiosity. He paid attention. He listened. And when he noticed a pattern, he chose to investigate it instead of ignoring it. That decision created a chain reaction. A small adjustment led to improved handling. Improved handling increased pilot confidence. Greater confidence influenced combat performance. The effects spread outward from there. Not dramatic at first, but real. History is full of similar examples. Many of the most effective wartime innovations emerged far from headquarters. Some came from factory workers, others came from maintenance crews, others came from soldiers, sailors, and airmen confronting practical problems in real time. That doesn't diminish the importance of engineers or designers. In fact, it highlights something important. The best results often occur when both worlds work together. Engineers provide structure, testing, and technical expertise. Frontline personnel provide experience, observation, and feedback from reality. Neither perspective is complete on its own. Together, they become powerful. Perhaps that is the most enduring lesson from this story. Innovation is rarely a solitary act. It is usually a conversation between design and experience, between theory and practice, between people building machines and people using them. The wire became important because someone noticed a problem. The improvements survived because others were willing to evaluate the evidence, and eventually, the results spoke for themselves. So before we finish, consider this question. If you had been there in 1943, who do you think would have recognized the problem first? The engineers studying reports thousands of miles away? Or the mechanic standing beside the aircraft every day? Let me know in the comments. And while you're there, tell us about another overlooked wartime innovation that deserves more attention. Sometimes the most fascinating stories aren't about famous weapons or legendary commanders. Sometimes they're about ordinary people solving ordinary problems in extraordinary circumstances. If you enjoyed this story, subscribe for more forgotten WWII histories, overlooked battlefield innovations, and the untold stories hidden behind the machines that shaped the war. Thanks for watching, and wherever you're watching from, let us know below. Until